Alright, let's rock and roll with another video. The topic of this video is going to be the computation of standard deviation. It's extremely important for your analytical chemistry class. You need to be able to do this to analyze data, and somewhere along the way you're going to encounter this in your class probably multiple times. It's a skill that you'll want to master. Did want to put together a video for it. Maybe some of you already know how to do this, but in case you don't, we need to learn. So that's what this is all about. So we're going to compute S, which is going to be called the sample standard deviation. It's actually different than the population standard deviations. Two different things. The sigma is the population standard deviation, and that is a measure of the standard deviation for the entire data distribution. Now in our case we have a limited number of data points, limited n, and because of that we compute the sample standard deviation. Sample standard deviation is computed through the equation that's shown here, and it is of course a very common measure of data set precision. You're going to see standard deviation in all kinds of measurement sciences. That's why it's important to master this skill, okay? So let's work a sample problem and see if we can make sense of this equation. Sometimes it's a little bit confusing, but it really need not be. It's pretty straightforward. So let's say that we have a data set in which replicate measurements yield four different values. These are four replicate measurements, so capital N here equal 4. We have trial 1, 2, 3, and 4, and it's whatever unit it is. It doesn't matter for our purposes here today, but those are just our measurements, and we want to know what is the standard deviation of that data pool. How are we going to achieve this? Well, there are a couple steps to success. The first step to success is going to be finding the data set mean. That's just the average of these four numbers. So you simply add them together, divide by 4 since we have 4 points. If you do that on your calculator, you'll find very quickly the average is 33.65. Okay, 33.65 is our average, or our mean. What do we do from there? Well, from there we can proceed by the computation, or with the computation, the standard deviation. We can use our equation for S. When I'm doing this, I like to write it out in the long form. If I'm not using my calculator, there are functions on your calculator that allow you to calculate S very easily. Maybe you want to master the use of those. That may be fine for common use in your course, but I wanted to work the problem out so that you could see how it's done. You can learn that, because it's also important. Sometimes you might not have that advanced calculator feature available, and you need to compute it long form. That's what we're going to do here. We don't need to be scared by that, because it's still quite straightforward. We just plug and chug using our equation. Of course, whenever you see the capital N in these equations, that's always the number of replicate measurements in our data pool. Here that's 4, so in the denominator I would have 4 minus 1. That would of course ultimately equal 3. In the numerator we have to do a little bit more work, because basically what we're adding is the sum of the deviations from the mean squared. We have one of these terms for each data point in our series of data. So here we're going to have 4 because we have 4 data points. I've only written 3 here, but ... That essentially means that sum is going to continue until you have one of these squared terms for every data point in your data pool. The reason why that is because what the equation for standard deviation tells us to do is, of course, add together the squares of the deviations from the mean. What does that mean? Well, it tells us to find the difference between each member of our data set. Here 31.2 is the first one, and the mean. So 31.2 minus the mean, 33.65, we're going to square that. I'm going to add a second term here for the next measurement, which was 33.7 minus the mean, 33.65. So that one was actually pretty close to the mean. I'm going to square that. Add that to a term for the third deviation from the mean, 34.6 minus 33.65 squared. Let's keep on going here, and next one is 35.1 minus 33.6 0.65 squared. Okay, so you see that for each data point, I have subtracted the mean. I'm going to square the result to get rid of any negative numbers should they arise. Take the square root of this fraction, and that's going to end up being my standard deviation. Okay. Now, at this point in the computation, if you're following along on paper, what I would kind of encourage you to do is to start by working out the mathematics of the numerator of the fraction first. All these differences in squares, because if you're doing this on a calculator and you can't do it automatically, there's a series of calculations that you have to come across, and then you have to add the results together. It's really easy to like push the wrong buttons or have the calculator get confused what you're trying to do, and that'll lead to the wrong result. So once I'm at this point, what I typically try to do, I'll move this up here at the top, continue the work, a separate sheet of paper. Let's zoom out a little bit here. Well, that might not work well. There. So what I'll typically try to do is to work each of these independently at first to try to reduce this fraction down in simpler terms, okay? Because it's really easy if you struggle with this to get confused with the calculator work. And boy, if you remember this equation and you know what you're doing, you don't want to get confused with your calculator and get to the wrong result, okay? So the first thing I would do is this minus this squared. And on my calculator, if I do that, I get a number that's a little bit over 6, okay? So that's just a result of this squared. And I'll do the second thing, this minus this, square that on my calculator. And this one was very small because there wasn't much difference. This minus this, squared it, got 0.9025. And then I would do this minus this and square that. And when I did that, I got 2.1025. Okay, so you can kind of see where I am trying to go with all this. And just simplifying my life, basically. Okay, so then we can add all these numbers together in the numerator. And if I do that, I get 9.01, a little over 9, still divided by 3, my n minus 1, still equal to s. But I've just simplified my life from something that's, kind of lots of numbers in this fraction, nothing too mathematically complicated or complex, but just a little bit tedious. You have to keep good records, so to speak. And I've reduced that down just to a pretty simple statement here. Okay, now if I go ahead and complete this by doing the division, I get a number, of course, a little bit over 3. That repeats on out, okay? And if I take the square root, I get 1.733 as my standard deviation. So that is going to be the standard deviation of my original data set that we talked up here, okay? So hopefully this has now simplified the process of the computation of standard deviation for you. You saw how we did it. It's just the square root of the sum of the deviations from the mean squared divided by n minus 1. This is a skill that you really need to know how to master. You need to remember the equation. It's typically not given to you on exams. Very, very important that you get this one down. Alright, thanks. We'll see you next time.